Hello, welcome to webinar 4, the fourth webinar in our Civil Society Data Partnership series. My name is Alistair Rutherford from the University of Stirling, and I'm leading the Civil Society Data Partnership project. For this webinar, we're going to be looking at some academic tools of data analysis, and in particular, some of the different software packages that are commonly used for working with data in universities, and how they're used and how that might be useful. So we'll start with an overview of statistical software and how it relates to academic research, and then we'll hear a little bit about 3 different packages. SPSS, Stata and R, with some examples of how they're used. And then lastly, we'll wrap up with a bit more information about the potential for collaboration with academics in data analysis, and that might give you access to some of these resources. So we have 5 presentations in total. As usual, you can make comments on the live stream page on YouTube, comments or questions, which we can answer as we go along. And you can also tweet using the hashtag ThinkData, and we'll try and respond to those comments and questions as well. So please do get involved. So our first presentation then by Paul Lambert is going to look at academic research and statistical software, and it should take around 25 minutes.
So first of all, let's talk about academic researchers and how they use statistical software. In the CSDP program, we're discussing the collaboration between academic and third sector researchers on the topic of understanding civil society. In earlier webinar sessions, we've discussed some commonly available and sometimes free tools of data analysis that we observe are quite often used by members of third sector research organizations, Microsoft Excel, for example. On the other hand, people in academic institutions, when they're undertaking the empirical analysis of data, they're probably much more likely to be using software that is specifically designed for the statistical analysis of data from social surveys, or from data structures that are similar in form to those of social surveys. So primarily numeric data, perhaps originating with questionnaire responses or with some other structured administrative data collection. Academics have been using research software since at least the mid-1960s to work in this way. And there's actually hundreds, ultimately, of different software routines out there, software systems out there that can be used for the analysis of numeric data, statistical software. It's often useful to distinguish between general purpose and specialist statistical software in this respect. General purpose software will ordinarily have capacity for quite a wide range of data analysis functions, and also functions that we tend to refer to as data management. So the processing and organization of data management, as well as generating results from the statistical analysis of data, so the data analysis functions. So there's a number of packages that are general purpose and provide both capabilities. There are also quite a lot of statistical software packages that can be thought of as specialist. And usually that specialism refers to particular type of data analysis functionality, perhaps a specific software designed to support, say, multi-level modeling, or perhaps structural equation modeling, 2 examples of somewhat advanced types of statistical analysis. Another important consideration, and it comes back time and time again in the sessions that we're recording for today's webinar, is the extent to which the software allows you to document what you're doing with data. In academic research and in research in general, we'd ordinarily aspire to the model of documentation for replication, which basically means recording what you do with data in a sufficiently clear way that you can repeat it at a later date, or indeed you could pass it on to somebody else and they could repeat it. So software that provides a replicable trail of what you do with the data, both in terms of data analysis and data management, is highly desirable. And that's easier to do in some software analysis contexts than in others. But certainly, most of the popular examples of academic research software do have the capacity for clear documentation for replication. To begin understanding how software is used to perform analysis of data, it's useful to understand conceptually the way in which software is used to apply specific tasks to specific data sets. Now, in most data analysis situations, what will happen is a user will have a copy of a data file stored somewhere on their local system. It might be on a drive on their actual desktop machine or laptop or whatever. It might be accessing a network location or a remote location that can be connected to their computer. They'll usually have a copy of the data, and typically they'll also have some additional documentation information about the data. Now, in most statistical analysis software, data is stored in a primarily numeric and tabular manner, such as is illustrated in this image, which shows the SPSS software of data analysis. So the main body of data would be the numeric values in a matrix-like layout, usually referred to as the variable by case matrix, where the variables refer typically to the responses to different questions from a questionnaire. The rows or the cases refer to the responses for individual units, individual people in this case. Now, most statistical software data files have more information than simply the numeric values. They also have associated metadata, labels for variables, for the values for particular variables. Other supplementary information is often stored within the data set in various forms of metadata. But the main work of analysis would ordinarily be exploring patterns of response, of statistical variations in the main numeric matrix of data. And a statistical software package will typically feature pre-written routines that allow the user to generate outputs that summarize the numeric patterns within the matrix of data. SPSS, for example, various ways to produce graphs summarizing the distribution of responses and variables within the data set. Here I'm just showing a histogram distribution of hours per week spent on housework based upon analysis of a single column, in this case, of the data set, the one labeled hours work. So statistical software simply works by having routines available that allow us to summarize patterns in the data and generate outputs from them. However, there is an extension issue, and it's an important extension issue. Generally speaking, when you're processing statistical software in this sort of way, you have the possibility of a command file format method for running tasks through the software package. That's what I'm trying to illustrate here in the image to the lower left of the screen. In this example is the SPSS software package. In SPSS, we have what's called a syntax file, which is a facility to list commands in a command language understood by SPSS that will run tasks on the data and produce results. So the syntax to generate a histogram, for example, is graph/histogram equals, and then the name of the variable that we want the histogram of. Several statistical software packages that are popularly used in the academic sector have quite useful syntax systems whereby many of the commands that are run on data are, you could say, human readable. They're reasonably easy to understand. They use words in English that we can often more or less work out what they mean. Obviously, knowing the meaning of code and finding out what code should be written requires further resources, help facilities. Typically, many people learn syntax by starting from examples provided by other people and applying them to copying and pasting them and applying them to their own data. But typically, there'd be a separate data file or a separate information file recorded and stored, which is the list of commands run through the syntax. And then the results of analysis, such as graphs and so on, are generated by running that syntax upon the component numeric data file. So why spend time describing command files and syntax? Well, they're very important to achieving good quality documentation of what you're doing. Most methodologists working with data resources would take the view that syntactical documentation of tasks performed on data files is highly desirable, almost essential to good quality research, providing a record of what you do with the data that you can easily rerun and repeat and make small modifications for if and when it's required. And later on today, when we look at particular examples of using software in particular contexts, we'll show illustrations of using syntax. We've got some syntax files available for you to download from the thinkdata.org.uk website as well. So, software in academic survey research. Sometimes there's a little bit of tension amongst academics because most people have their favorite software package and really dislike other packages that aren't their favorites. Sometimes there's a bit of a battle between people over which software to use, perhaps in a collaborative team or in terms of purchasing licenses. And there's quite a lot of software out there that people sometimes make use of. We're going to concentrate on three general purpose packages: Stata, SPSS, and R. And I have to be honest and say that I'm one of the many people that has a favorite. My favorite is Stata. So it could be that some of the materials I'm presenting are rather biased in favor of my own favorite package. But there's different qualities, different strengths and weaknesses to different resources. Stata and SPSS as well are general purpose packages that are generally regarded as fairly easy to use in that they have syntactical language that is human readable and fairly concise. But they also have a considerable range of functions, both for data management and for data analysis, that can be achieved through understandable software commands, syntax commands. Stata began as a popular package in economics within the social sciences, and perhaps in the last couple of decades has spread widely to other social science disciplines. And it's very popular at the moment amongst survey researchers in particular, in North America and increasingly in Northern Central Europe, for example. In my opinion, it's becoming more and more the dominant package of social survey research, or the analysis of social survey research data sets. R is a very different package compared to Stata and SPSS. R is a freeware. Stata and SPSS are proprietary. You need to buy them. R is a freeware that also has a very wide range of capabilities, but it isn't used as much by applied researchers undertaking survey research and comparable analysis, primarily because quite a lot of the things it does require rather complicated programming, quite difficult programming to achieve. When we look at R in detail, you'll perhaps be able to see the relatively less intuitive character of the way in which the generic package works to apply tasks to data resources. This has many attractions and is very popular with statisticians, for example, and methodologists, because it's very flexible. It supports an awful lot of different and original types of data analysis, as well as, of course, being available for free, which means collaboration between people in different circumstances is potentially more feasible. But for applied researchers, R is a very difficult package, arguably, to use, although we'll show some examples and ultimately you can take your own view on that. SPSS and Stata are very different to R. SPSS, like Stata, is a popular package used a lot by applied researchers with a number of user-friendly features, including command language that is reasonably easy to understand and apply. SPSS probably used to be the dominant statistical analysis package amongst survey researchers in many countries. Possibly that situation is changing in the academic sector as other packages such as Stata are becoming more popular. But SPSS is still widely available. For example, the majority of universities in the UK will have licenses, site licenses to SPSS, and they'll teach students how to use SPSS, for example, in research methods courses. So it's still a prominent and important package. Just for completeness, I've mentioned one other package in this slide, something called MLWin, which is a specialist software. One example of many different types of specialist software designed for a particular purpose. In this case, fitting a type of statistical model known as multi-level models with random effects. So MLWin is an interesting specialist example of software. MLWin is free to not-for-profit users in the UK. If you're interested in multi-level modeling, I would strongly recommend going to the Centre for Multi-Level Modeling website where MLWin is distributed from and looking at some of their resources. But for today's focus, we're gonna stick with the three major general purpose packages, SPSS, Stata, and R, and say a bit more about those in time. One other interesting development in software that it's worth just highlighting to you, perhaps as I'm describing the existence of lots of different software packages, some of which are free, some of which are proprietary, you might be wondering about the efficiency of this. Wouldn't it be better if we could all just use the same software package? Or could there be a tool developed to allow people to do analysis in consistent ways across software packages? There have been some efforts to make generic software in this style. And one example, which is an academic research project in itself from the UK, led by researchers at the University of Bristol, the Centre for Multi-Level Modelling, something called StatJR, which is an integration exercise in statistical analytical software. It's basically an interface for opening up data sets, specifying statistical models to run on the data, and then generating command in different software language and running the analysis in different softwares. It's very interesting methodological development. The idea is to take away the technical requirement to have specialist expertise in software programming in order to implement different software tools. It provides a web-based interface to specify the model and the data set that you want to run, but then you can essentially choose which software package you want to run the analysis on, and it will automatically generate appropriate code in that software package, provide you with the code, run the code on the software if you've got the software locally installed, and provide you with the results. So an interesting, ambitious methodological undertaking in interoperability between different software packages. So working with software, it's really important to try and use syntax to take control essentially of what you're doing with the software. we mean in this sense is that when you write out word by word the specific commands that you're running on the data file that you're working with, you have a much clearer record that can be communicated to other people of what you're doing with the data. But you'll also feel and be in a situation where you can see much more clearly what you're doing and make changes, correct mistakes, make adjustments to the results of analysis. So, although perhaps I sound a bit like a broken record in making this point, but if you want to make good use of analytical software for research purposes, you're much, much better off if you can write out commands in the syntax language. Typically, as I alluded to before, you don't have to remember all these different words, the language of the software package, in this case SPSS. You don't have to learn these words in order to be able to apply them. You would typically take examples from other syntax files, command files, and copy and paste and change variable names. Most software also has facilities for generating appropriate syntax to do a task, whether from help menus or from drop-down options or from a variety of sources. Also, online supporting resources with information about how to use software effectively will have resources to allow you to work with syntax. And this develops into the theme of good quality documentation of the tasks that you're doing. Sometimes in social research, we refer to workflows, characterizing the steady development of tasks and processes applied to data, which can be readily achieved through command files, through clearly annotated syntax files. One nice feature, if it's not already obvious to the syntactical construction of command files in software, is that as well as writing out commands that do things to data sets and are recognized by the language that the software language that we're working with, it's also easy to annotate the command files with comments for your own information. Again, the code that's on screen at the moment is from SPSS, and in SPSS, any line beginning with an asterisk is treated as a comment. It's not an active command, but a comment, typically that you yourself have written in for your own information. And those lines without a star are active commands that do things in SPSS. Now, if you have access to the sort of software package that runs in this way, that allows you to send commands through syntax to run on the data, it's really compelling to do so, and there's not a great excuse for not doing so, in the sense that it's easier, really, to work with syntax than not. You're also doing a much better job in building up a workflow documentation of what you've done with the data. As you become more sophisticated in using software through command files, the chances are it'll be convenient to break up the lists of commands into separate subfiles. And typically you can call upon one subfile within another. Within the example on screen at the moment, there's the line include file equals path2 BHPS voting codes.sps. What that code means to SPSS is, at this point, find another syntax file, another command file, and run it. That's the one that's in the indented box here. So at this stage in the code, it'll actually open up another file, run its contents, and close it again. And this can be a good way of organizing long and complicated jobs, splitting them up into subfiles in this way. We often refer to the master file as the main file that includes links to subfiles within it in order to achieve a workflow of data analysis in this way. There's lots of examples of syntax available online. One project that we also had at the University of Stirling, dames.org.uk, provides, amongst other things, lots of examples of downloadable syntax files in different languages that you can look at as examples of documentation with workflows. There's lots of other ways to find syntax online by Googling in whichever software package you're looking for. One last point to make about working with software for doing data analysis in the social sciences. There are a variety of approaches to data analysis, or a variety of techniques of analysis that are available to us. And quite crudely, they can be characterized as ranging from simpler descriptive and analytical techniques to rather complicated analytical statistical techniques. Simpler analytical techniques are typically the things that are somewhat more widely known. They involve generating descriptive statistics, perhaps averages, percents, cross-tabulations, two-way tables, bar charts and line graphs, and so forth. Obviously, the simpler methods are more widely known. They're probably easier to communicate the results from them, and they have important qualities that they can be very attractive ways of summarizing patterns in data. However, the simpler techniques have their problems. There's a real risk of ignoring more complicated processes and mechanisms and patterns in the data if we restrict our summary to a two-way correlation, for example, or to a simple bar chart. We may well be unduly simplifying our characterization of the social patterns that we're trying to summarize through statistics. Often, actually, inappropriately simplistic statistical summaries give a bad impression because they can sometimes be quite obviously wrong as a summary of the wider social process. And these can be the things that make people very suspicious of social statistics and evidence based upon statistical analysis eventually. Unreasonably simplified data is quite problematic. So generally, people working with the analysis of data would often say that it's usually appropriate to also make use of more complex statistical analytical methods that try to take account of the complex range of factors involved in a social pattern, make adjustments for complexities in the data, typically statistical models that take account of patterns in quite a few different variables at the same time. Now, complex analytical methods, as I'm describing them here, are harder to understand, harder to implement, and harder to communicate to other people. But it doesn't mean that they're not more appropriate in many analytical situations. This simple division between simple and complex methods, well, it's obvious enough, and it's a part of any sort of communication, any analytical communication. But it is important to thinking about academic software or research or statistical software that can be used for undertaking research. It'll tend to be the case that the sort of software used in the academic sector typically does support the specification and implementation of more complex analytical methods, statistical models of a more challenging format. And that will not necessarily be the case for some other tools of data analysis that are often used or widely available, perhaps free online analytical tools or popularly available tools, which are not so easily adapted to exploit more complicated statistical summaries. So a great attraction of exploring and making use of the analytical academic research software is the capacity to use both simple and complex analytical methods, whereas some other tools available for statistical analysis might be much more limited in terms of moving to the more complex end of the analytical spectrum.
So we've heard there about the key role that statistical software plays in analysis for academic research. And in particular, the idea that might be new to some people is the role of syntax in the workflow. So keeping a good record of your analysis and the steps that you've taken in the form of syntax files. That's a key element in each of the software packages that were discussed, and in working with data in this way. So what we're going to go on to do then is to see some examples from each of 3 software packages. And these will make use of syntax files, and the syntax files with the examples will be available on the website, along with the slides as normal for this webinar. So you will be able to download those syntax files and have a look at what that workflow looks like, and how the commands work, and follow along as you're listening to the example. So we'll start by looking at some examples using the package SPSS. It's the first of the 3 packages that we'll look at, and this talk is about 20 minutes.
Okay, so now we're going to talk about a particular package for statistical analysis. We're going to talk first about something called SPSS, which was first used, I believe, in 1968 for sample survey data analysis, and has been going strong actually ever since. It's a popular tool of statistical analysis in the social sciences. SPSS itself, well, it used to be branded as the statistical package for social scientists, SPSS. Actually, the software company that runs SPS, now IBM, no longer uses that particular acronym. SPSS is a product name in itself. SPSS has been updated regularly since its inception, including developments for different types of operating system, and including substantial version upgrades. We're now on version 23, available in 2016. And over the last few decades, we've moved through more than a dozen versions in recent times. I'm going to make a few points about SPSS, and then I'm going to try and show an example of analyzing data in SPSS. SPSS is a proprietary package. If you want to use it, you'll have to buy it or become part of an organization that has a license for SPSS. If you go to IBM SPSS webpage, you'll find information about licensing options and purchasing. An important consideration for academic users is that the majority of universities are likely to have a license for use of SPSS by their members for academic research purposes. So if you are affiliated to a university, certainly in the UK, you're probably entitled to use SPSS for access as part of your university affiliation. What's shown on the screen are some images of the SPSS interface. The more recognizable one, perhaps, is the data editor screen in the lower half, which is the matrix of numeric data that's the core data file in memory at any particular time when you might be using SPSS and on which statistical analysis is undertaken. Now, when you want to work with data resources, you'll typically undertake data management and data analysis tasks applied to those data resources. And I've been stressing throughout, it's much better practice if you can use syntactical commands to do things with those data resources. There are other means of doing things in SPSS, but we won't tell you about them just now. They basically involve point and click on icons and drop-down menus, but they're not a good idea. Using syntax, on the other hand, we run specified commands on the data resource. We generate syntax, perhaps by using a previous example. One popular thing amongst SPSS users is an option to generate syntax through a paste option in some of the commands available from drop-down menus. So you might set up a command with a drop-down menu, but rather than clicking on OK to run it, you might click on paste, which would give you the syntax code that will run that command in your syntax file. And that can be quite a popular way of finding appropriate syntax to do things with data. It's quite easy to get help in using SPSS. There are really quite a lot of textbooks that describe the use of SPSS for research, but not so many of them have extensive coverage of syntax commands. For syntax commands, you probably want to look at various online locations. One of the most popular, but by no means the only, useful online source of software guidance in SPSS and other packages are the UCLA statistical computing resources. The Institute for Digital Research and Education at University of Los Angeles, California. University of California, Los Angeles. If you go to SPSS, the SPSS page within that resource, you'll see a variety of ways to find out about using SPSS for data analysis, including introductory starter issues and tutorials and guidance, and then command file illustrations, syntax examples in a number of different languages. So let's have a look at actually using SPSS for a particular bit of analysis of data. If you open up SPSS, if you've got it on your machine, the first thing you'll ordinarily see is the data editor window. So this is, at the moment, it's a blank window. I haven't loaded in any data or opened up a command file. But what we would typically do next in working with data, or what we would do if we're being good, is not open up a data file, but open up a syntax file, which we're going to use to run commands with. File open syntax here to open up a syntax file. I've got one that's sort of lined up and ready to go. This is downloadable from our thinkdata.org.uk website. This syntax file contains textual comments. The lines begin with stars are just comments for my own notes, and active commands that do things in SPSS. One thing to note, if you're using SPSS syntax, commands can be spread across multiple lines, but lines must always end with a full stop, or the end of a command must end with a full stop. So this bit of code here is one command. This bit of code here running over two lines is also one single command, going from the word get through to the full stop at the end of the word UK2. What we're doing in this example is analysing a UK survey called the British Household Panel Survey, which you can download yourself from the UK Data Service. It's a large and complex social survey, freely available for secondary research use for not-for-profit purposes. BHPS has some data about volunteering patterns amongst many other features within its data resources. I'm going to run a few different lines of syntax. One of the first lines I'll run is a somewhat more complicated line. It basically sets an alias to tell me where the data files in the BHPS are. Basically, it says, after running this line, when SPSS encounters path 1 or the exclamation mark in path 1, it'll actually read the full location of where on my local machine a secure copy of the BHPS is stored. So to run this bit of line, to run this particular line, send it to SPSS as a job, I highlight part of the line, and I can go run selection. Control R is commonly used for this purpose. If I click run, that job is sent to SPSS. We switch automatically to the output window and we see the outputs of that command. There isn't any additional output other than an echo of the job that's just been submitted. Let's run a couple more lines. I'm gonna run several different commands at the same time. The first line is get file, and that means open up a data file. It means open up this particular SPSS format data file and keep these particular variables within the data file. I found out which variables I could use by looking at the BHPS documentation. We've then got a couple of commands that will be run on that data once it's opened, descriptive statistics on all of the variables, and a frequency distribution for one of the variables. Then we're going to change the missing value declarations for that variable and rerun the frequency distribution on it. This has worked fine. You might have seen a quick warning message flashing up on screen. That's just about a rather specific feature of the formatting of the data file. It doesn't mean we haven't opened up the file. If we look at the data editor window, it's now got, this is the data from the BHPS that we've read in. It's just a handful of different variables, but it's quite a large data set. 14,419 cases in this data set. So the output that we've run, we asked for descriptive statistics. This is just summary data on the numeric values of all of the variables in the data set at the moment. Frequency table for a variable called R-lactal, which is a question, how often do you do unpaid voluntary work? At least once a week, at least once a month, several times a year, once a year or less, never, almost never. In the initial version of the data, the value -7 for proxy and or phone is a response for people that weren't asked this question, typically because it was a phone interview rather than a face-to-face interview. So one thing we do in SPSS is a bit of data management to say, treat the -7 as missing, which basically means once that's been declared, when we produce results, -7 will be excluded. And if we rerun the frequency table after that, we see a slight difference in format. The valid codes are just the range from 1 to 5. So just trying to illustrate some aspects of using SPSS to do some data analysis. We'll have a quick look at the tasks involved in producing a simple regression analysis, one type of slightly more complicated statistical analysis. There's quite a lot of data preparation involved. I've labeled it in the code file the data management phase. Regressions have some requirements about the particular format of the variables involved. First, we're going to choose as an outcome variable a 0-1 dummy variable coding of the volunteering question. If you notice the distribution of responses on the volunteering question, most people were not volunteering, and then there was a moderate number who were regularly or semi-regularly. I've decided at this point to branch together the categories 1, 2, and 3, which were people that were volunteering at least a few times a year or more often, and then the nevers and the very rarelies together. And I make a new variable which is either got the values 0 or 1, 1 if you were in the categories 1 to 3, 0 if you weren't. And that's going to be the outcome variable in the modeling approach. There's a few things that I want to consider as explanatory variables. I've got measures of gender, age, education level, and region. These are the variable names in the BHPS data that indicate these properties. And for all of them, I'm going to need to make small adjustments to the properties of those variables in order to get them into a sensible regression analysis. I won't talk through all the processes in the next lines of code, but we're basically generating new variables that have similar qualities to the original indicators, but are more statistically appropriate for putting into an analytical model. Dummy variables, if you're already familiar with that phrase, we're generating dummy variables to indicate, for example, whether or not a respondent is female, whether or not a respondent has a high level of education, whether or not a respondent comes from Scotland, for instance. And in the case of a measure of age, we're leaving that in its numeric form, but we're restricting the analysis to people who are aged 18 and above. So if I run that bunch of commands, a load of things get run to the data. At an endpoint, we've got these revised variables, a variable called fem, which has values of 0 or 1. Basically, it's a 1 if you're female, 0 if you're male. High qual and Scotland are similar, a 1 if you've got high qualifications, a 1 if you're from Scotland. Age is the numeric value of age in years of individuals in this survey data set. So a typical data analysis here would be a logistic regression. What are the relative influences of those 4 different factors upon the probability that you say you volunteer often or fairly often? This first line runs a logistic regression for this purpose. If you're not used to looking at regression outputs before, well, good luck in trying to understand all this different code. But basically, logistic regression is a device for summarizing the joint relative influence of a number of different explanatory factors upon an outcome. And the way it's read in its simplest form is by looking at the values of these estimated beta coefficients for the explanatory variables and asking whether or not they're statistically significant. They'd be significant if the value of the significance term is less than 0.05 by conventional criteria. So actually all 4 of these variables are significant. And what that's saying is that in general, there's a significant influence of being female upon whether or not you volunteer often or regularly. Because it's a positive coefficient, the evidence is that in general, being female increases your chances of volunteering regularly. And the contribution from the regression framework is that this is a result that's net of any influence of age or education or living in Scotland, for example. So in general, being female makes you more likely to volunteer, even after you can control for differences of age or education level. Positive coefficient for age in years. So in general, being older makes you more likely to volunteer regularly. A positive coefficient that's significant for the effect of having a higher level of qualification. So in general, being better qualified makes you more likely, on average, to volunteer often or regularly. Finally, a negative significant coefficient for living in Scotland. So in general, net of these other factors, if you live in Scotland, you're less likely to volunteer regularly than if you live somewhere else in the UK. That's the finding from this result. Surprising, maybe. Could be exciting, but there's one more thing that it's worth showing because it will change our results slightly. If you heard of survey weighting, a complicated survey like the BHPS is not a simple random sample design. It's a stratified random sample design with disproportionate representation of some subgroups. So it's much more appropriate to do analysis using survey weights, which readjust the influence of responses according to known features of the underlying population. In our data set, we've got a variable called RXRWTUK1, which is a weighting variable, which is designed for this purpose. The distributors of the BHPS provide this with the survey to allow us to reweight the data and get appropriate results. Now, sometimes weighting doesn't really impact the results of analysis? Sometimes it does. I've just rerun the model, but with weights switched on, and I get slightly different results, slightly different beta values and significance values. The effect of gender, age, and education is actually the same as it was before. Women are more likely to volunteer, older people more likely to volunteer, people with high levels of education more likely to volunteer. But there's a difference in the interpretation or the evidence about the impact of being in Scotland. There's a negative coefficient, but it's not statistically significant. The significance value isn't less than 0.05. So after controlling for weighting, we no longer have compelling evidence that Scotland is definitely associated with lower average levels of volunteering, controlling for other factors. In the first result, it looked like there was this pattern. In the second result, it's not so clear-cut. So a complicated story from a complicated analytical method. So that was just trying to summarize some features of using SPSS for research purposes. There's 101, well, 1,000,001 things on the web that can help you also in learning more about SPSS and using SPSS for research purposes. It's a popular, commonly used package that can generate all sorts of analytical methods or use all sorts of analytical methods to survey and survey-like data. The only thing to really stress in this presentation is you'll be in a much better position if you work with SPSS in the syntax interface, recording your commands as you go along. It'll be much more productive, much more reliable, lead to higher quality results if you can do this, rather than if you use alternative ways of generating results from the analysis of SPSS.
So in that presentation, you've got a good example of one software package, SPSS, and the different steps of analysis, of working with the data, and in particular of using syntax files to record the commands and manage the workflow. And you've seen some examples of the sort of outputs and types of analysis that the software can carry out. As we've heard, SPSS is just one software package, one that is quite widely used, but there are others as well that are also used that have different advantages and disadvantages. So we're going to see now another example, another software package that's quite commonly used and that works in a somewhat similar way, but has other potential features, and that is Stata. So we'll see some examples using Stata in a talk that will last about 15 minutes.
But about a different software package for analyzing data, something called Stata, or Stata. It's pronounced differently by different people. Stata is a popular statistical analysis package, originating in particular in economics, but increasingly used across social science research disciplines. If you go to the Stata web pages, you'll find out about different ways in which you can obtain a licensed copy of Stata. Again, in general, most people working at universities have probably got access to Stata for research purposes. The majority of universities in a country like the UK will have some licenses for Stata for people to use for their research purposes. But it's perhaps the case that Stata is a bit less systematically available across higher education institutions compared to another proprietary software package such as SPSS. On the other hand, Stata does have quite a few different models for accessing for purchasing copies of Stata, including some relatively low-cost individual license options, such as for people working in the academic sector or not-for-profit organizations. Stata has many similarities with SPSS in how it works with data and the way in which it does things. But it does have slightly different functionality. It has some options for statistical analysis that generally are a wider range of options and include some more sophisticated techniques of analysis, arguably, than within SPSS. The Stata interface, I'm trying to show it on the screen at the moment. Primarily, the thing you would see as a user would be an output window where results are generated and a command syntax window where you write out commands in Stata to send to be processed on the data. Usually, by default, an image of the underlying data is kept hidden from the user unless you specifically ask to see it. In contrast, for example, to SPSS, where you might be used to the data editor window where you're actually looking at the numeric data from the start. In a moment, we'll look at an example of running syntax on data files. In general, the syntax language of Stata would often be human readable. You can often deduce more or less what the analysis code is doing. In general, though, you don't learn the code yourself or memorize things that you can do with code. You typically learn ways of finding the appropriate code, such as through help files, through example software providers. UCLA Statistics, again, have a wealth of examples of code in Stata to do things with data. And there's some really good textbooks out there that outline Stata syntax and ways in which you can do analysis with Stata. Stata actually, in particular, its help files are particularly well organized and easy to use for understanding appropriate syntax for running tasks on data sets. So if you are working with this package, it's often the case that you would just, if you didn't know what the tab command meant, for example, you would just write into the interface help tab, and you get a very accessible description of what's being done. The syntax commands in Stata are widely referred to as do files simply because the extension used by convention for storing these plain text files is .do. So we often talk about running do files in Stata. And we'll have a look now at doing some stuff in Stata with a real-life survey data set. Here I've got Stata 14 opened. You can change the way Stata looks. If you yourself have a copy of Stata, probably the default presentation will be white format output rather than black. I happen to prefer it the other way around, what's known as the classic interface. But with these things, you're free to choose. I've also resized the windows slightly from the default settings. But the output window is the thing that would be immediately obvious to you if you're working with Stata. Now, to use Stata effectively, the thing to do once you've opened this software is to go and open the do file editor. And then within the do file editor to open up your the command files that you're going to work with. Again, I've got a pre-prepared example file of code, which is downloadable from the thinkdata.org website. Asterisks in Stata mean comments that aren't active commands. Control-D or execute in the language of Stata would be submit a particular line for running to Stata. Send that line as a command to Stata. If I submit this line of code, I'm running Control-D with the keyboard. It just gets echoed. It's a comment. It's not an active command. The file we're using here was also used in a workshop that we had a couple of weeks ago at the University of Stirling, illustrating using secondary analysis with Stata. Again, some of the first lines in this particular file are a tiny bit more complex. We're going to declare a number of aliases that are going to last through the current session. The global command is essentially, if we're defining aliases, it's going to read, when it encounters path 1, it's actually going to read a location on my computer where a data file is stored. We're going to use something called the European Social Survey, ESS, round 1, which you can download for free for not-for-profit use from europeansocialsurvey.org. I've also got a couple of other paths, somewhere that we can potentially save outputs such as graphs generated by the session, somewhere where we can save temporary copies of files if we need to. This is a common task when processing data files through software. So highlight those 3 lines, and I'm going to run with the keyboard Control-D to send them to Stata for processing. Those commands have been run. We don't see any additional outputs, but they have been processed. Now, one thing to note in a Stata file is that commands don't naturally spread across multiple lines unless you specify them. The end of the line is also the end of the command. If you don't want this to be the case, if you want to break up a command over several lines, there's a few different tools you can use, but most commonly 3 // tells Stata that this command extends over 2 different lines. So describe and then a list of variables using an ESS data file. That's going to extract some metadata from the ESS data file without actually opening it up in local memory. It's just going to summarize data from that file. Control-D to run it. We get a list of variables within that data file, just the variables that we've asked for. We're going to use these data files, we're going to use these variables in analysis below. These aren't all the variables in the data file. They're just a selection of those that we had picked up on from the documentation. I'm going to do a couple of commands that will take a moment to run in Stata because the file is relatively large, and Stata sometimes processes data files in some locations. In this case, it's a network file location where the data is stored. It takes a second or 2 to run. So if I run these 2 lines here, which open up the data and display metadata on it, it's just going to pause and take a few seconds to actually run that on the relatively large data set. But there's nothing to be worried about in itself. The first command, use, is essentially open up this file. So use these variables using this data file here. It's truncated on screen, but it's the ESS.dta data file. Then num label all add, that means add numeric metadata, number labels to outputs from results. So we're using the European Social Survey. We're going to look in particular at a variable called imparvo, which is an attitudinal question, an attitudinal response where people answering the survey were asked, to be a good citizen, how important is it to be active in voluntary organizations? In this copy of the data, we've got 42,000 respondents, and these are from about 15 different countries in Europe, actually. 2,000 of them said volunteering was extremely unimportant. 3,000 of them said it was extremely important. And we've got quite a nice spread of different opinions about the importance of volunteering here. So we've got something interesting to work with. We've also got within the data some invalid categories, don't knows and no answers, coded with specific numbers. One of the first things we might do in the analysis is take out the missing categories, 77, the 88, and the 99. In Stata, recoding the variable and to a value which begins with a dot is a convenient way to indicate missing codes. So if I recode that variable and say the value is 77 to 99, reformatted and become just .m, that changes the underlying data. And then if I rerun the tab command, the missing values have been cut out. They're not shown by default unless we actually ask for them to be shown. Some of these commands that are running are making adjustments to the values of variables within the data, setting them up for analysis. I won't talk through all of them just now, but the endpoint will be the construction of two modified variables, the Impavo variable, which is ranging from 0 to 10, and is the responses on how important voluntary participation is. We've also made a new variable called any_VW, and this is for the 42,000 BHPS European Social Survey respondents. This is measuring whether they report that they've undertaken any voluntary work recently. Now, as ever with secondary survey research, using software to analyze data, there's quite a lot of preparatory work, data management, preparing variables for analysis. Not just the outcome variables, but we've got a number of explanatory variables that we think might be important. And I've got some lines here which are processing the data to set it up for subsequent analysis. One key factor, the European Social Survey dataset, is understanding the variable country, which country the responses are from. We've got string labels for the different countries that are providing respondents to data in this analysis. I think I'll just run over these lines without explaining them any further. Send these lines for processing. One or two of the component lines take a moment or two to run, just simply because we're working with a big data set. One of the things I looked at was a bar chart showing the average age, the average value of time spent watching TV across different age groups. This is the result of the graph bar, mean TV tot over age, just to see what the relationship between those two factors was as an explanatory exercise. But I won't dwell on that. A few interesting lines here, rather complicated lines, but interesting ones to highlight. Always with social survey, we've got challenges of missing data. We've got different volumes of response to different questions. Actually, in this command here, codebook, you can see the output, the variables we're going to use in the analysis, but there's different numbers of cases with responses with valid non-missing responses to the different variables. So sometimes cases aren't included because they didn't give a valid data, for example, for years of full-time education. Now, a little bit of code in Stata to generate indicators of how many different variables individual cases have missing values on is shown in the RMIS example. Egen RMIS equals ROMIS, and then a list of variables. What that does is it makes a new variable called RMIS1, which has as a value the number of different variables on which that case has missing values for all of these different possible variables. When we look at the frequency distribution of that new variable, there are 40,452 with no missing values on any of those variables. There are 13 cases with missing values on 4 of those variables at the same time. So probably our analysis is going to proceed on the 96% of people in the data set with no missing data on any of the variables. But we might take different strategies, perhaps, to summarizing these results. The example file then goes on to look to doing some data analysis on these results. And I think I'll just look at one line, a regression model, which is just for the UK. We're doing regress, views upon the importance of volunteering, explanatory variables are gender, age, education, but we're only doing it if the respondents are from the UK and if they don't have any missing values for any of those variables. Run that line, regression results, what sort of things influence having a higher or lower numeric value of the variable in parvo, which, if you remember, was a 10 for feeling that volunteering is very important, a 0 if you don't think it's important at all. Regression results, the story of the regression results, people who are female as compared to males, net of age and education, are more likely to think that volunteering is more important, and that's statistically significant. Also for age, significant and a positive effect. So people with who are older in terms of age will be more likely to think volunteering is important. Effect of education, though, not statistically significant. P-value is more than 0.05. So it's not clear that education is distinctively related to how important you think volunteering is. Now, the code file does show a few more activities of analysis. And we do the same regression model, for example. Here it's the same regression model for Sweden. So one thing we might do is a comparative exercise. How do the relative influences on volunteering vary between Britain and Sweden? If we look, for example, in Britain, being female was associated with a significant positive coefficient, which means that women in general would say that volunteering is more important. And in Sweden, that wasn't the case. The coefficient isn't statistically significant. So in Sweden, there isn't a clear difference between men and women in how important they think volunteering is, whereas there is a clear difference in Britain. So bit by bit, these bits of empirical data about social patterns, in this case, influences on views about volunteering, can contribute to building up an evidence base about, in this case, civil society volunteering patterns. So that was a brief highlight of things that you can do with Stata, the way Stata works as an engine, essentially, for doing things with research data.
So we've heard there about a second software package, Stata, which has some more advanced features for working with data, and seen some more examples of the types of analysis that you can carry out. And I think it's useful to compare the different software packages and see what's different, what's similar, and the different features that they have. So hopefully these examples give you a chance to get a flavor of that, and which sort of software might be appropriate for different applications. Now, both SPSS and Stata are software packages that you need to purchase licenses for. The third package that we're going to look at is an open source package, and so is available to download freely, but is also quite powerful and has some challenges in working with it. So this is the software package R. We're going to get an introduction and overview and some examples in R in a talk that will last about 10 minutes.
Last talk, looking at specific software packages in this webinar, is looking at a rather different package to SPSS and Stata. We're going to look at R now, which is a freeware rather than a proprietary package. R is a general purpose analytical package that can do all sorts of things with data, but it does require a level of programming that's more advanced than is required in Stata and in SPSS. To install R, rather than have to go and buy a copy, find or join an institution that has a licensed copy, for example, it's a few simple steps in downloading the package, and yeah. Wasn't expecting that today. But go to the R webpage, rproject.org. You simply need to download an exe file and run it on your computer to install R on a local machine. It's freeware. That does mean it's distributed without any warranties or promises that it will work reliably. It's a GNU freeware framework, but obviously this is very appealing to people in certain circumstances. If you don't have the infrastructural access to SPSS and Stata and packages like that, you can immediately download R and use it as you wish. The R interface is available in a variety of flavors. On screen, I'm showing two popular examples: the default R interface, and also something called R Studio, which is these days a very popular alternative freeware interface for doing things with R. R Studio is, and the default R and R Studio work in very similar ways, but most people that use them would feel that R Studio is that bit more convenient, that bit easier to work with. It's almost essential with R to use syntactical commands. There are a few possibilities to not do so if you're determined, but almost everybody working with R to analyze data is writing code in R and working in that framework. We're going to have a look at some examples of using commands in R in a very simplified way. The example we'll show is a rather artificial one associated with a book chapter that I wrote on different software packages. It's just a couple of exercises in opening a small data set and processing it. R is substantially more complicated than other statistical packages, but not impossible to master and to use. And there are some good textbooks out there that describe ways of using R and various online resources where you can get guidance and suggestions on how to learn R code. R, SPSS, Stata, other popular packages of analysis, all information on them available through UCLA Statistics. A popular alternative web page for guidance on R is the QuickR website, which attempts to provide rapid access to commands to do both more simple and more complicated analytical exercises in R. Once you start using R, you'll realize that even simple and quick resources are still quite complicated by comparison to other packages, but there are options available out there to help you through the process. So let's have a quick look at using R. I won't spend too long on it, but just a couple of examples. First image on screen is the default R. If you download R directly, this is what you'd see. You'd actually just see initially the R console, which is an interface where you can write in commands in R. ls means list any objects in the data at the moment. What people would typically do would be open up a script file, which is a syntax command or a command file, in order to run jobs in R or write out commands in R. I'm going to use the CSDP webinar 4 file, which is downloaded from our website. I'd actually already got that file open here. I'm just bringing it up to the front here. In R, the hashtag symbol serves as a comment. You have to highlight the whole of the line that you want to run, and to run the line selection, Control R will generally do the job. So that just sends those hashtags to the interface to run. Nothing happens in this case. Now, R is that bit more challenging than SPSS and Stata perhaps, but it can be understood. It's important to understand that R is what's called an object-oriented software package or language, which basically means you define objects, and objects could be data files, but they could also be bits of text or the results of analysis, such as a table of results. You define objects and then you display them in addition if you want to. So the first line here is a slightly more complex line. It's essentially an alias specification, but we're going to name an object called file2, a new object called file2, which is going to be the textual value listed here, which is the location of a data file on my local computer. So file2 becomes, as dot character, the textual value of this. So if I run Control R to run that, now file2 is now an object in my R session. I've got one object so far, and it's file2. If I just ask to list, if I just write out file2, we'll just get a list of what that object is. Now file2 here is a bit of text, but it could be a numeric data set. It could be 20,000 cases long or something. In this case, it's a single line of text. I'm going to skip one line, but an important thing to know about R is that the majority of tasks that you might be doing with R will draw upon libraries. Now, libraries are extension routines to the basic R functionality that allow you to do useful things with data. Libraries refer to installed packages that you might have installed locally on your machine. In some cases, some packages will already be available by default, including the Foreign is a package that's very commonly used and has a capability of allowing you to read into R data files that are stored in the formats of other software packages, such as Stata and SPSS format. So if I run the line library foreign, what that does is says that from now on in this section, commands defined under the subroutine library foreign will be available to us. So basically the foreign package is a list of specialist commands that aren't available by default, but we've now asked to make available to the session. So the first command I'm going to do is I'm going to make a new object called anon-data, and it's going to be the result of an activity called read.dta applied to file2 with a subroutine specification convert.factors equals f. What on earth does that mean? It means use a functionality, read.dta, which is actually associated with the foreign library and means read a Stata format data file. The thing it's going to read is file2, which we've defined just above as this thing, HIDRM, anon server data. So it's going to read a Stata format file with this location here. And it's also going to ask it not to convert variables in the Stata file that have textual value labels into textual values. It's going to keep them as numbers. That's what convert.factors equals false means. So I'll run that. What have I done wrong? I haven't put the data file in the right location. Bear with me. I've made a simple mistake in locating the data. It's probably useful actually to show me correcting this mistake, because it's a very typical sort of thing that happens with our users. The data file is actually at this location, CSDP data. Control C to copy that. I need to rerun my as character line here. And you might notice as well, and this is a common mistake for R in using R on a PC, but the direction of the slash symbol for directory specifications that R needs is in the opposite order to what we would default to in Windows. It needs to be a /, not a backslash. So I need to substitute this for this. I'll do it in a slightly more thorough manner in terms of syntactical documentation. Rather than delete the original line, I'll comment it out. Now I'll rerun that declaration that file2 refers to this location. And I nearly forgot to add the actual file name. So the thing that will be file2 now refers to this location. And I forgot to delete 2 quotes. I'll leave these in because it's useful to illustrate how easy it is to make mistakes, perhaps, in R. So file2 is now a different bit of text. It points to a file that actually is in that place on my computer. So now, if I go back to that line, anon data equals read.dta file2, we don't get the error message. It's worked smoothly. We don't see much by way of output, but a new object has been read into the data called anon2. Sorry. Called anon_data. And this is some results from a large secondary survey file, an object that has a bunch of data in it. Commonly, to summarize a data file, the names command in R or the head command. Names lists the names of the variables in the data file. Head lists the first, in this case, the first 6 rows of the data file only. Let's just look at 2 analytical results. Table, anon data, $hours work. What this will do is look at the object anon_data. Within it, it'll focus on the variable called hours work. That's what the $ symbol means. Pull out that part of the object. And the table command is just a simple way of summarizing the distribution of values for that variable. It's hard to read, but the table means there are 42 cases with the value -7, 13 cases with the value -1. It's complicated, but here we're actually seeing there's 10 cases with the value 18. There's 1 case with the value 98. This is hours of work. Hist will generate a histogram on the basis of that variable in the same way. A couple of cases with high numbers, most people between 10 and 30 in terms of hours of work. It's actually the variable in question. You have to take my word for it, but the variable in question is hours spent on housework per week. So most people are reporting about 10, 5 to 10, some people 20, some people 30, 40, few people 100. So hopefully by that little example, you're seeing the way in which R does things with data, but also perhaps a slightly more complicated way in which R specifies objects and variables within objects and can run analytical commands, but very frequently by drawing upon underlying libraries. As well as the basic R interface, it's also worth being aware of R Studio, which is also a freeware and for most people is regarded as a slightly easier to use interface to running R than the default setting. If I run the same bits of code, and again, I'm going to need to change my labeling here to CSDP and /data. highlight the line, Control Enter, sends this to run. The command interface down here in RStudio, what it understands as file 2 just before. Convenient thing with RStudio is easy access to help resources, summary data, plots generated by the analysis, information about the packages available currently, the packages installed that we could use. Slightly easier handling of results. Most people that use R for analytical purposes would use RStudio or some similar alternative freeware for processing the package as over and above the use of the R interface. But everything's otherwise working in the same way in the basic R and RStudio, but many people prefer RStudio as a slightly more convenient tool for analyzing data. So that was just a quick look at the freeware package R, another tool that can be used for analyzing statistical data sets and is sometimes used by social scientists in this way.
So that's given you a good overview of a third software package, R, which is available free as open source, is a powerful package, but has some more can be more challenging to work with and to get to grips with. We've now seen 3 different software packages that are widely used in academia to work with data. And while it can be challenging to have the resources, the skills, the capacity to work with data and to work with this sort of software, there is potential to collaborate with academics using these resources in order to conduct research and to analyze data that you hold as an alternative to getting hold of this software and working with it yourself, or potential to access this software via a university. And one of our aims of our project is to encourage that sort of collaboration. And so we're going to have a brief talk now about the potential for third sector organizations to get access to some of the resources in universities as part of our planned affiliate scheme. And this talk will take about 5 minutes.
One last point we want to highlight in thinking about software uses for analyzing data. In the CSDP project, where we're thinking about collaborations between people in the academic sector and people in the voluntary sector, the third sector, in using data and undertaking research, we're very conscious of the fact that the academic infrastructure brings with it the possibility of using data resources and information resources such as software that are just not necessarily available to people in third sector organizations. And in many situations, it might be desirable that people working in third sector organizations can also use the same tools of analysis, but infrastructural arrangements, as they are at the moment, don't make that a simple thing to do. But there are a variety of routes through that. There's lots of opportunities for research collaboration between people in the third sector and people in higher education organizations. In general, the people working in the higher education sector would need to obtain some level of research income, some grant income, or some sort of funding to justify a substantial amount of research input. There's quite a wide range of ways in which money can be used to support research projects of this collaborative nature. And these would range from quite substantial amounts of money, or wads of cash, as I'm trying to illustrate in the slide, to quite low-cost ways of facilitating collaboration between the two sectors in terms of research exercises. One consideration as a possibility for people thinking about doing research and civil society and in collaboration with third sector research resources would be Research Council's UK funding opportunities. So this is government funding available for original social scientific research. The Economic and Social Research Council, for example, social science research funders, will encourage research collaborations, in particular, that exploit secondary data resources, the Secondary Data Analysis Initiative, encouraging people to use secondary survey data sets, for example, and other forms of data resources for research purposes. And they're keen to promote collaborations across sectors and impact of academic research in non-academic sector. So some of the ESRC funding opportunities would be very amenable to a productive and original research collaboration between academic and third sector researchers. Secondary analysis in general, it's useful to be aware that making use of existing data sets, whether that's deliberately collected survey data sets or administrative data generated by third sector organizations themselves or other related organizations, is generally appealing to funders because it's high value for money. It doesn't cost much to reuse the data, but high quality results may arise. And in that tradition, there are appealing opportunities for comparative research as well, comparing over time or between countries social patterns related to civil society on the basis of typically of secondary data resources. So one of the things that would often appeal to academics would be pursuit of a significant amount of funding for undertaking research through a major government sponsor such as RC UK or a comparable funder of research. But there are actually other intermediate ways to get research projects going that involve a little less financial outlay in different ways. There are other agencies that fund research, perhaps on a slightly smaller scale than major government organizations, but charities in Scotland, perhaps the Carnegie Trust is one example, that will provide money for original academic research, particularly in if there are promising looking collaborations such as between third sector and academic researchers. And actually many academics are in a position to a certain extent to undertake research as part of their standard posts with limited need for additional money. So sometimes it's possible if you're in a third sector organization looking for somebody to engage in research with, you may be able to get an academic to work in an unfunded capacity. There are some other collaborative opportunities for undertaking research between the sectors that involve bringing people together in different ways at relatively low cost, but would often have the attraction of bringing people in the third sector within the higher education institutional setting. So I'm not sure I said it before, but a key motivation of collaboration in this data analytical context is that as part of a collaborative team, researchers in third sector organizations would often be able to make use of software facilities and other infrastructural resources at the university context. So sometimes, for example, funding a PhD studentship at a university. So if a third sector organization made a contribution to a PhD studentship, this would be a relatively low cost way of getting high quality research undertaken within the higher educational institutional environment. And sometimes people in third sector organizations might also be able to enroll on specific training courses within universities, such as particular taught courses or an MSc project or sponsor an MSc student to do a dissertation on a project, for example. All of these also provide routes into higher education collaboration. And then we have another possibility at the University of Stirling. I'll talk about in a sec, the affiliate membership scheme for third sector researchers. So people interested in third sector data, in third sector organizations, are often a major barrier for them is the lack of higher educational infrastructure or support, such as access to software, file store, library resources, colleagues available for consultation easy. Collaboration with staff in higher educational institutions on research projects or through things like a sponsored PhD is one possibility. Sometimes historically, members of third sector organizations have arranged bespoke membership of universities, such as an honorary research appointment within a university, which is something that's often possible. If you've got a colleague in the university who's keen to work with you, they might be able to make an arrangement where you become an honorary researcher at the university and can then use the university infrastructure in that way. As part of the Think Data project, we're trying to develop a slightly more systematic and organized way for members of third sector organizations to undertake not-for-profit research, taking advantage of university infrastructural research resources. This would involve making relevant people members of the university, in this case the University of Stirling. They'd be affiliate members, and we're trying to develop a scheme, AMSTA, the University of Stirling Affiliate Membership Scheme for Third Sector Researchers, which is basically a device where people in third sector organizations who are interested in academic research will have the opportunity to apply for membership, to apply for affiliate membership at the University of Stirling, which will give them the possibility of using resources associated with the University of Stirling for their research purposes. This scheme's under development as I'm speaking. It's not completely resolved, but we'll be putting updates on the thinkdata.org.uk website as this progresses. We're very hopeful that this will be a very powerful or very useful route to collaboration between academic and third sector researchers in this framework. So watch this space for more news about hamsters.
So that concludes our final presentation of the webinar this afternoon then. It should have, hopefully it's given you a good overview of some of the key tools that academics use for working with data, and let you see some of the potential of the different software packages and what's the pros and cons of each of them, and illustrated this idea of syntax files and of having a good workflow for working with your data. And then lastly, then we've heard a bit about the potential for working more closely with academics, and the scheme for Scottish third sector organisations that we're trying to set up as part of our Scottish Civil Society Data Partnership. Remember that all the resources for this webinar will be linked in the description below and can be found at our website at thinkdata.org.uk. And there you can also find details of our future and past webinars on a range of different topics to help third sector organizations make better use of data. Thank you for listening.